Okay, so thanks for the message that in my acid-base properties of water video, it went this weird blip at like 2 minutes and 34 seconds. So this little video is to fill in that blip. So what I had started talking about was sort of shorthand notation for an acid-base reaction with a weak acid. And so we can represent a weak acid as HA. And it'll react with some base. We'll just use water as our base right now since it's amphoteric. It can go both ways. And we know that if that's going to happen, our weak acid will donate a proton to our base. And so that will allow us to form our hydronium ion as well as our conjugate base, which is whatever's left over from the weak acid after it donates its proton. So when we look at this, and since it's a weak acid, we know that most of the molecules are going to stay together. So although we will release some protons to form hydroniums, again, most of the molecules are going to hang on to our proton. So we want to be able to talk about how many molecules is that? How strong is our acid? So acid strength is described as how easily that proton is donated. The more protons that are released, the stronger the acid. So for acid strength, we represent how easily that proton is donated using the acid dissociation constant, which is Ka. So that's a big K, so that's an equilibrium constant. And we can write our equilibrium constant as the concentration of products over reactants. So we've got our H3O plus and our A minus divided by the concentration of weak acid. And we know that water doesn't get included in our Kas because its concentration is 55 molar. It's a liquid. So its concentration is not going to change much. So we leave those things, liquids and solids, out of our expressions for equilibrium constants. So this is our acid dissociation constant, and the way you interpret it is that the larger the Ka value, the stronger the acid. That means you have a larger numerator, so more products produced, which means more protons have been released, so that's a stronger acid. Now sometimes looking at the Ka, since the numbers turn out to be quite small, and most acids are relatively weak, it's kind of hard to just deal with such small numbers. So instead, we take the log, or minus the log, of the Ka value, and whenever you have minus log, that's the same thing as little p. So minus log of the Ka is our pKa value. So our pKa value is also going to be the more common way that we talk about the strength of acids, and its trend is the exact opposite, so it's logarithmic. So that means that the smaller the pKa, the stronger the acid. So that's what you missed in that little blip, and then it goes on in the rest of the video to talk about water and the ionization constant of water. Sorry about that.